Hello, so in this video we're going to start talking about the different cases which we can have for this Euler equation. Okay, so here's the Euler equation here. And basically what we do is we try and solve, we guess a solution of the form y equals x to the power of r, and we've shown that if we guess a solution of x to the power of r, then we basically end up with something that looks like this. So we end up with something that looks like this. F of r is equal to r squared plus alpha minus 1 lots of r plus beta. Okay, set it equal to 0. Okay, and basically then we just try and solve that quadratic. Okay, and then we'll end up with a value for r. We'll end up with two values for r. Okay, now the first case we're going to look at is when r1 is not equal to r2. Well, r1 not equal to r2, that's a really nice easy one to solve, because remember that we're looking for a general solution. Okay, y of x is equal to c1, so some constant times y1 plus c2 times y2. Again, it's just some linear combination. Okay, it's just kind of the same thing that we're looking at, with all of our other differential equations. Okay, so basically what we're doing is we're trying to look at some general solution that looks like this. Well, if y is equal to x to the power of r, okay, if y is equal to x to the power of r, okay, and if we end up with two solutions that r1 is not equal to r2, then that implies that we'll end up with two solutions as well. So sorry, we end up with two values for r, implies that we end up with two solutions as well. So y1 will be equal to x to the power of r1, okay, and y2 will just be x to the power of our other r, so x to the power of r2. Okay, so these are our two solutions. Okay, and therefore we'll end up with y of x is equal to c1 times y1, which of course is x to the power of r1, plus c2 times y2, which of course is x to the power of r2. So this is our general solution now. This is our general solution that we end up with just from our two solutions when r1 is not equal to r2. It's nice and simple. We have also talked about linear independence from the Vronskin, haven't we? So, there's no reason why we can't do this. We don't have to do this, but, there's no reason why we can't. We've got the skills now, we might as well employ them, might as well show off. So are these two solutions linearly independent? Well, remember what the Vronskin was. The Vronskin was our first solution and our second solution, okay, and then to form a 2 by 2 matrix we also need the first solution differentiated and the second solution differentiated, and we take the determinant of that, and that's our Vronskin. Okay, and if it's not equal to 0, then it's linearly independent. In other words, our y1 could not be written in terms of y2, or vice versa. So one solution cannot be written in terms of the other solution. Okay, so let's just plug in our y1 and y2. Well, y1 was x to the power of r. Y1 is x to the power of r1. Sorry, x to the power of r1. Okay, and y2 is x to the power of r2. So y2 is x to the power of r2. Okay, then just differentiate this. So what do we end up with? We end up with r1 times x to the power of r1 minus 1, and differentiate this thing, so we end up with r2 times x to the power of r2 minus 1. Okay, so just literally differentiate that. That's the Vronskin. Let's just expand this out because it's a determinant. Okay, so we've got, what have we got? We've got x1, maybe if I use a different colour because we've got lots of red going on. So x to the power of r1 times r2 times x to the power of r2 minus 1. So we've got x to the r1 times r2 x to the power of r2 minus 1, okay, and then subtract, because it's a Vronskin, this thing times this thing. So we end up with subtract, let's see if I can just move this over, there we go, x to the power of r2 times r1 x to the power of r1 minus 1. So let's just expand this thing out. So we end up with, well, let's just simplify this thing first of all. So we end up with, if we just look at this thing, are you happy that, if I just take this r2 and stick it out the front, so in other words I just write it like this, just swap these two things around, so we end up with, what is this one, r1, okay, are you happy then? This is just going to be the same base being multiplied together, so therefore I can just write it as x to the power of r1 plus, because I'm just going to add the powers, because of course we're multiplying the bases together. So this is we're going to end up here. Okay, do the similar kind of thing here if I just swap these two things around. So I've got r1 times x to the power of r2 and times the two things together. Exactly the same scenario got on here. So it's just like, if you didn't quite get it the first time around, if you have 2 to the power of 3 times 2 to the power of 6, that's just the same as 2 to the power of 3 plus 6. Okay, just add the powers together. So I'm just doing exactly the same thing here. So this is now going to become r2 plus r1 minus r2. So I've got exactly the same thing again if I just swap those two things around, because again I'm just just adding them together, so it doesn't matter what order I do them in. Okay, so therefore I've got the same thing there. I've got the same thing there as I do there. So therefore I can just take out I can just take them out as a factor, and I'll just be left with R2 minus R1, R2 minus R1 times x to the power of R1 plus R2 minus 1. Okay, and let's just have a look at this thing. Well, my first condition was, you know, I'm looking at the case when R1 is not equal to R2. So because R1 is not equal to R2, when I subtract them, I'm not going to cancel. Okay, if they were the same, they would cancel. So therefore, that would be 0. But because they're not the same, then they're not going to cancel. Okay, so I'm going to end up with this thing isn't going to go to 0. Okay, what about this thing here? Well, anything raised to a power, okay, can't be 0 unless that thing that's being raised to the power is 0. So, for example, if I have 2 to the power of n, okay, then that can't be 0 ever. Okay, regardless of what that power is up there, it's always got to be positive. That's always got to be positive. Okay, but if I have, say, 0 to the power of 2, then that's obviously going to be equal to 0 because I'm just squaring 0. Okay, so as long as this x here isn't 0, then this thing here isn't 0 either. So in other words, this here isn't 0 as long as x isn't 0. So as long as x isn't 0, therefore the Vronsky, this Vronsky is not equal to 0. So the Vronsky is not equal to 0, therefore it's linearly independent. So I can basically say that my two solutions are linearly independent. Providing x isn't equal to 0. Okay, and I mean there's plenty of examples out there which are going to show. I'm just showing you the theory for the time being because that's fairly straightforward to understand.